Autonomous vehicles are complex systems. Developing and validating them is not a trivial task, especially for off-road use cases. The first set of challenges arises at the development phase, where the design complexity can quickly overwhelm the engineers, leading to ad hoc, opportunistic, or potentially uninformed design choices. The second set of challenges arises at the validation phase, where the complexity of unstructured off-road environments, combined with the static and dynamic variability, seems like an intractable problem. Additionally, the constraints associated with physical development and validation, including the space, time, and cost for designing and testing, granular control over design and test parameters, and the safety of people and assets involved, only add to the list of challenges. We propose to alleviate these pain points by combining the power of digital twins and model-based systems engineering within a coherent digital engineering framework developed using AutoDrive and MATLAB Simulink. Going forward, we will see how this systematic, streamlined, and completely traceable framework enables informed design choices and operational design domain specifications with data-driven credibility. Let's look at a typical off-road autonomy use case, where the stakeholders want an autonomous RZR capable of performing visual servoing, automated emergency braking, cruise control, hill hold assist control, and weather-adaptive light control. An engineer can quickly ideate this as a high-level concept, which can then be formally described as a system architecture in System Composer, an MBSE add-on to MATLAB Simulink. The engineer can then start implementing the different components as model-based designs, right within the system architecture abstraction layer. First, let's focus on the simulation component. We leverage the AutoDrive ecosystem to develop a high-fidelity digital twin of the target vehicle, the Polaris RZR Pro R4 Ultimate. To ensure the accuracy and reliability of this digital twin, we calibrated it against its physical counterpart. For this purpose, we collected over 4 hours of off-road autonomous driving data using the real RZR. This data was first used to digitally reconstruct the operating environment with sub-millimeter precision. Subsequently, the vehicle dynamics model was optimized through time-synchronized open-loop data replays to match real-world trajectories within half a wheelbase tolerance. Finally, we verified the correlation between state input pairs across real and virtual datasets to ensure a real-to sim fidelity of over 97%. We developed a custom API to enable bidirectional, real-time communication between AutoDrive and MATLAB Simulink. The core API implements an object-oriented WebSocket protocol, and we were able to harness the potential of Level 2 MATLAB functions to create custom blocks that seamlessly integrate the API with Simulink models. The components and subsystems of the autonomous driving software were also implemented as Simulink models right within the system architecture abstraction layer. Particularly, deep learning models for object detection were coupled with planning and control systems to enable perception-enhanced control of the RZR in off-road environments. Requirements Editor, Variant Manager and Test Manager were used for traceable requirements engineering, efficient variant management, granular parameter sweep setup, systematic test case definition, and automated execution of the simulations with a single click. Here, we put the off-road autonomy algorithm, along with its variants, through 128 test cases constituted of distinct times of the day and weather conditions. The hands-free execution of the 128 simulations took roughly 7 hours, representing a 70 to 85% reduction from the previous duration of 1 to 2 days. The test results and key performance indicators were logged in the Data Inspector, and a 2,184-page detailed test report was exported automatically. Such data can, for example, be used to analyze a single test case in depth by associating various KPIs with the requirement satisfaction criteria. Alternatively, the aggregated test results can be analyzed to inform design choices and define the operational design domain with data-driven credibility. The true power of this digital engineering framework lies in its scalability and extensibility. For example, within just few hours, we could apply the same framework to develop and validate a new off-road autonomy use case comprising a different vehicle, ClearPath Husky A200, a different sensor suite, GNSS plus IMU, a different environment, open uneven terrain, and a different task, point-to-point autonomous navigation. Moreover, this framework can also be applied to systematically develop and validate autonomous vehicles across scales, configurations, and operational design domains. All in all, the powerful integration of AutoDrive and MATLAB Simulink created an end-to-end framework for off-road autonomy development and validation. We have published our findings in a conference paper and released the APIs and examples presented in this video as open-source software with the hope that it will allow engineers to design and validate autonomous vehicles more systematically and credibly. Thank you.